This is NEAF Talks.
And I know that was then. This is now. NEAF 2023 begins, and thank you very, very much for coming. Have a great weekend, and we'll see you again next year.
Welcome to NEAF 2023. We are really excited that you're all here today. We thank you for your patience over the last several years. Before we get started with our speakers, I want to take this opportunity to recognize the folks at Rockland Astronomy that have made this program and programs for today and tomorrow. They're really going to be spectacular, as Joe said. So can I give a big round of applause for Ed, Mies, Karen, Joe, Sarah, Frankie, and all the volunteers we have here supporting this program. So give them a big round of applause. And so now it gives me great pleasure to introduce our first speaker. He's been exploring the cosmos and took his first image of the moon in 1959. He has thoroughly enjoyed speaking at conventions and gatherings where astronomers are there. As Joe said, he's published many, many articles in astronomy, sky and telescope, deep sky. And his today's talk, Postcards for the Moon, provides a very detailed description and image that he provides daily for all of us. Please give a big round of applause welcoming to NEAF 2023 from San Antonio, Texas, Robert Reeves.
Welcome, Thank you. Thank you very much. Well, I can't tell you how much of a thrill it is to be here. This is my second time on the NEAF stage, and I'm a little bit less nervous this time, so I'm going to have some fun. A lot of you have come over. I work for Celestron. I'm at the Celestron booth. I'll be there for the next 2 days. So if you have any questions about the moon or anything about Celestron itself, come over and have a chat with me. If you have any questions about the presentation here and you can't get your question in later, I'm available at the Celestron booth. The Artemis II crew has been announced. We now know who the next humans to go to the moon will be, including a Canadian. So interest in the moon is going to be ramping up considerably. But when you get right down to it, in the past half century since Apollo, much has appeared in the media about how we got to the moon, the politics of why we went to the moon, and about the personalities who engineered and controlled and actually did the moon landings. But when you get down to the basics of it, after half a century since humans last set foot on the moon, how much does the average person really know about the moon? Well, surprisingly little, unless you're a very passionate lunar astronomer like me. So I'm going to try and help you out with that today and explain a little bit about how the moon came into being, how its face evolved, and let you become friends with the moon. Once you understand the face of the moon, it's not just this boring place with bumps and holes that you see in an eyepiece and, oh, okay, that's the moon. The moon will become your friend. It'll become a friendly target that I hope you go back to and observe. So I've been in love with the moon my entire life. And my earliest memories of the moon were watching moonrise through the window when I was a young child. And that memory has always stuck with me. And today, the space explorations that have revealed all the science about the moon have not stripped away the wonder and mystery I felt for the moon before the space program. Now, there's a name for people like me, and it is not lunatic. No, I like to adopt the name selenophile, a person who loves the moon. And I hope that you'll get a little bit of twinge of that love after you understand a little bit more about the moon when I'm finished here. Now, some of you may know me from my astrophotography days where I wrote a series of books for Wilman Bell. In 2000, we came out with wide field astrophotography. It was well received, but it was right at the tail end of the film era. We didn't realize that at the time, but digital overwhelmed us very quickly. So I wrote a second book in 2005, Introduction to Digital Astrophotography, the first book written about that subject. In the meantime, although I'm well known for my lunar photography, I do enjoy deep sky photography. I do that from my backyard in San Antonio using very aggressive light pollution filters, so I can get excellent results from home that I used to have to travel a 200-mile round trip. But continuing on, in 2006, I published Introduction to Webcam Astrophotography, which I like to think triggered the the planetary camera industry. My moon photographs have appeared in various periodicals and publications, some articles of which I've written myself. If you have the popular Backyard Astronomer's Guide, Volume 4, leaf through it, all of those moon pictures are mine. And all the pictures we're going to be seeing this evening, or today, are all taken by me. Now, I've spent the past 20 years spending an awful lot of time chasing large telescopes across the southern United States trying to take high-resolution images of the moon. But I find that I can do a better job in my own backyard with small telescopes because the small telescopes aren't affected by the bad seeing that is prevalent in central Texas. I use a Celestron 8 down in the lower right. That is my very first Celestron that I bought in 1975. It still works wonderfully. I use a Celestron 11, and I also cheat a little bit, even though I work for Celestron. I use the Skywatcher 180 millimeter Maksudov, also a very wonderful planetary telescope. People ask me, well, how good can the amateur astronomer do with lunar photography? Now, the thing I'm holding on the right is a plate out of the famous Kuiper Lunar Atlas. Back in the 1960s, when we were gearing up for Apollo, that was the definitive lunar research atlas, photographic atlas. The image on the right, left, taken through my own Celestron 11 from my own backyard. It's the same region, except it's north up. The old atlases were printed south up. But it's the same area, and you can clearly see that the modern amateur telescope today outperforms what the professional did back during the heyday of Apollo. Any of you can do this. The equipment is sitting out there on the NEAF floor, and everything you need is there. Now, I like to say I have no special talent. I'm not a trained astrophysicist. I don't have a degree in astronomy. I'm just curious and very passionate about what I do. And the fact that you're here at NEAF says you are too. So I hope you join me. My playground is the moon, and I invite you to come out and play with me. So, when I was young, the moon was a big deal. This is back during the Apollo era. The moon was a dream, a goal, a destination, but still a place of mystery to be explored by brave heroes who dared to ride a pillar of fire and set foot on another world. But then, in the mid-1970s, there was a fundamental change in amateur astronomy. Very lightweight portable telescopes like the Celestron 8 became very available, and people were able to get out of Dodge and get out to dark skies. We weren't limited to our backyards with big, giant, clunky Newtonian telescopes. And the moon kind of faded from our dreams. Deep sky became king. Well, I'm here to try and revive our interest in the moon. So the presentation of my goal here is twofold. I want to bring the moon back within your astronomical realm and make it something that is not to be avoided because it's the big bright light in the sky, blocking out deep sky, but something to be embraced and enjoyed in its own right. And I want you to not just look at the moon, but to understand the moon. So, today, some astronomers consider the moon a boring place, a place covered with bumps and holes. But the moon is not visually static. It's a geologic wonderland that changes night to night as the shadows change, revealing the phases reveal different features. It's always changing different every night. It is not a static target. There's much to enjoy and see on the moon if you know what to look for. So I want you to go back to the moon with me and rediscover its wonders. Now, so today, we're going to look at the creation of the moon, the evolution of the moon, the creation of the face of the moon, understand the various forms of its geology, and explore some sentimental lunar favorites. Now, obviously the earliest event on the moon was the creation of the moon itself, which we now theorize as the collision between two protoplanets, perhaps 20 million years after the evolution of the solar system. These two planets collided. From the debris, our Earth evolved, and the moon evolved from a ring of debris around the Earth that was perhaps 10 times closer to where the moon is today. The moon is slowly receding away, moving out about 2.5 centimeters per year, which means the moon is now about 1 meter further away than it was when Apollo 11 landed on the moon. So the early moon, a molten blob, so to speak, took me a while to solidify. All the heavy elements sunk to the middle, the silicates floated to the surface in a global magma ocean. But finally the moon solidified, and we began a series of time epochs. Now on the Earth, we measure geologic time. Remember back when we were kids and we were thrilled with dinosaurs and we had all those cool names, the Jurassic period, Triassic, Cretaceous and all that. Well, the moon has similar geologic times, beginning with the pre-Nectarian, which was shortly after the moon solidified, the Nectarian period, where the massive basins on the moon were created by huge asteroid impacts over a very brief period of time. Then there was the Imbrium epoch, where there was massive volcanism that formed the Maria, the dark features on the moon that formed the face of the man of the moon. And then a long Eratosthenian epoch, where a majority of the craters, post-Nectarian craters, formed. And then finally the modern era, the Copernican epoch, going back to about 1 billion years ago. And the division from that is any crater on the moon that has a ray structure has to be less than about 1 billion years old. It's a Copernican epoch, because crater rays fade in time. As micrometeorites till the soil and solar radiation alters the chemistry of it, crater rays fade. So if you see a crater that has a ray structure, it's a fairly young one. So, moving on back to the Eratosthenian epoch, the moon looked much different than it does today. There were no maria, there was no extensive volcanism. It was just a cratered wasteland. The crater formation rate back at that time was about 300 times higher than it is now. So the face of the moon was being altered tremendously because there was literally just a lot more buckshot floating around in the solar system that we were colliding with. So all the large basins were formed during this time, but there was not yet any Mare-forming volcanism. During the Imbrium epoch, extensive volcanism, continuous eruptions and lava flows slowly filled in the basins over a period of millions of years, and the dark regions filled in the low-lying circular basins. Now then the more modern Copernican epoch, just within the past 1 billion years, a significant reduction in impact rate, which is a good thing, otherwise we might not be here. And of course the craters formed during this period still have the beautiful ray structures. Now, it boils down to two things. Any feature on the moon has been formed by only one of two processes, either impacts, creating a crater or a basin, or volcanism that subsequently modified it or created a feature exclusive to volcanic activity. So, start off with the Maria, the dark regions on the moon. The Maria are sometimes called the lunar seas because early on in the telescopic period, the observers thought these dark areas were oceans, but they're not, of course. And these are volcanic deposits, basalt deposits, deposited in the low-lying basins that were blasted out during the Nectarian epoch. The basins and the Maria lying within them are not the same thing. You have to understand that a Maria is the basalt deposits in a basin. The basin and the Maria, two different things. The basins were created by asteroid impacts. The Maria were caused by lava flooding. And not all basins have lava fill in them. There's 50-something basins on the face of the moon backside as well. but not all of them have been lava flooded. Now, the Maria define the face of the moon. They create the caricature of the band of the moon that we see at moonrise. It's what's created all of the romance, the prose, the poetry over the years. Very beautiful apparition. There are 21 named Maria. 11 were named by Giovanni Riccioli in the 17th century when the initial mapping of the moon began, and 8 were named in the 19th and early 20th centuries, and 2 were named during the space age, during our lifetime. So the map of the moon is very dynamic. It's changing all the time. The common theme of the lunar Maria is they're round. Mare Crisium, Mare Nectaris, a prime example. Mare Crisium, again, round. It appears egg-shaped because of the perspective on the close to the limb of the moon. Mare Serenitatis, again, circular. Serenitatis, the Sea of Serenity, perhaps one of the least cratered areas on the moon, thus one of the most serene, very smooth. Mare Imbrium, the Sea of Rains, visually appears to be the largest of the Maria, forms the man in the moon's left eye, but it's actually the second largest. Oceanus Procellarum is bigger, but because it's so slant view, inclined view on the western side of the moon, it doesn't even contribute to the face of the man on the moon. Again, humorum, the theme, round impact basins filled with basalt. And as I mentioned, Oceanus Procellarum, actually the largest of the Maria, twice the size of Mare Imbrium, covers 2 million square kilometers of the moon, but it's so foreshortened on the western limb that it doesn't contribute to the features of the man in the moon. Now, not all of the basins completely filled with basalt. On the backside of the moon, the crust is thicker, so it restricts the volcanic eruptions. Along the limb of the moon, Mare Austral, never completely flooded, so it ended up being a collection of basalt-filled craters, so a very mottled appearance down the southeastern portion of the moon. Other Maria don't necessarily lie within a single basin. Frigoris goes across the northern part of the moon and kind of forms the eyebrow above the man in the moon's eyes. It lies in portions of 3 separate basins. 1,800 kilometers long, but only 200 kilometers in height, lies in portions of the Procellarum, Imbrium, and Serenitatis basins. Now, lunar mountains are formed differently than they are on Earth. On Earth, we have tectonic activity that builds mountains, erodes them away, our weather, our plate tectonics, oceans erode mountains away, and new ones form in their place. Mountains don't last on the Earth more than 100 million years or so. But on the moon, it's a completely different process. Every mountain range on the moon is actually the rim of an impact basin, and it's been in place for the past 4 billion years. The mountains on the moon, once formed, stay that way. A very static process in that case. Earth's mountains renewing every 100 million years or so, mountains on the moon remaining there for 40 times longer, unchanged. Now, the rim of the Imbrium Basin, the eastern rim of the Imbrium Basin, is the most common source of looking at mountain ranges on the moon. Up near a Plateau crater, we have mountains, and then there's a break by Cassini crater, and we pick up the Caucasus Mountains. Lunar mountain ranges are named after terrestrial mountains. And down toward the south, the Apennine Range points like a finger down to Eratosthenes crater. And then finally down at the bottom, just above Copernicus crater, we have the Carpathian Mountains. Now, these all arc around Mare Imbrium and are the raised outer rim of the Imbrium impact basin. Now, one of the lunar mountain ranges, the Cordillera, is the outer impact ring around the Mare Orientale on the western limb of the moon. We can only see that one night every lunar month. The Terminator shadow doesn't reach this area until one day before full moon. So this mountain range is in shadow until just before full moon. You see it one night as the shadows are visible behind the mountains. One day later, it's full moon, those shadows are gone, the mountains vanish. So the Cordilleras play peekaboo with us. Others like the Jura Mountains, a smaller impact basin overlaying the rim of the Imbrium impact basin, but you can clearly see the effect of the round impact basin rim creating these mountain chains. And not all of the prominent mountains on the moon have a name. There's a surprisingly large number of features on the moon that are not named. For instance, the mountains on the western side of Mare Imbrium, they have no name. Now, types of craters on the moon. You think a crater's a crater, it's a hole in the ground. You think of it like a pothole at the road that you run over. But no, there's different kinds of craters. Now, just like stars are classified in a main sequence from the blue stars to red stars, with our sun being in the middle as a yellow star, craters on the moon also have a main sequence. If a crater is less than 16 to 21 kilometers in diameter, the physics of the impact just create a simple bowl-shaped crater. But if it's significant larger impact and creates a crater larger than 16 to 21 kilometers, it completely alters the appearance of the crater. The rebound of the rock, the subsurface rock, springs back up and creates a central peak, and the strength of the lunar crust isn't sufficient to hold the mountains, the walls, and they collapse into a series of terraces. Now, if the crater is larger than 300 kilometers, it's no longer considered a crater, it's a basin. Examples, simple craters like Helicon and Leverrier up on northwestern Mare Imbrium near the Jura Mountains. Complex crater, prime example, Copernicus. We're looking straight down on it, the beautiful central peak easily visible. We see how the collapsed terraced walls tumble down to the inside of the crater. And then Bailey, originally classified classically as a crater, but now we know it as a basin because it is larger than 300 kilometers in diameter. Now, classic examples of complex craters, they all feature a central peak and collapsed terrace walls. Pythagoras up in the northwest, Geminus up north of Mare Crisium, Moretus down in the southern part, all have the same features, the central peak, collapsed walls. Now, crater rays catch our eyes. We can see these from Earth with our naked eye. The ray structure around Tycho, the cluster of rays up on the northeast side of the moon, we can see those with our naked eye, even though we can't see the parent crater. But the crater rays are made from pulverized glassy material blasted out from the explosion that created the impact, that created the crater. And this pulverized material is very good at reflecting light back toward its source. So at full moon, when Earth is lined up between the sun and the moon, that is reflecting directly back at us. And these crater rays show up very well. Now, like I said earlier, if you see a crater with rays, it's less than 1 billion years old. It's a fairly new crater in geologic timescale. Tycho has the largest system on the moon. Rays on Tycho span over 2,200 kilometers. But it has its share of mysteries. Notice the railroad tracks going up to the northeast. They're parallel and they do not converge in the center of Tycho. That's a bit of a mystery. If somebody can explain that to me, we'll probably get your name on a research paper. Now, monodirectional rays, such as those extending from Messier and Messier up at the upper left, or the butterfly ray pattern, like around Proclus, these indicate a very oblique, shallow impact. And there is no ray material splashed back in the direction the impactor came from. So there's quite a few butterfly ray patterns on the moon. Secondary craters, created by the material blasted out of the primary explosion, showers out on the moon. The big lumps create additional craters. Now, these are not as deep or as articulate as the primary impacts because their impact velocity is low. If it blew out of the crater and fell back to the moon, it did not reach escape velocity. So it cannot be any faster than 2.4 kilometers per second versus the cosmic velocities of 20 or more kilometers per second for the primary impact. So these small secondary craters fan out in a pattern creating very small craters splattering out from the primary crater. Not all craters are round. Here's examples. We've got Hazel up at the top. Looks like a peanut. It's actually two overlapped craters, independent craters, merged into one. The same with Rhea E. Multiple impacts that give the impression of elongation. But Schiller, that's another story. Schiller is so long that if its length were translated into the diameter of a round crater, it would be one of the largest craters on the moon. But it is a single oblique impact that plowed this extremely narrow, long channel. And again, craters are not round, and as Emanuel makes this heart shape up on the north part of the moon, it's overlapping two craters. Meton, my good luck charm. 4 overlapping craters that look like a 4-leaf clover. Agrippa and Godin, the one on top, bullet shaped, the one on the bottom, shaped like a bell. There's all shapes of craters on the moon. Another type of crater are floor fractured. These started out as your standard complex crater, central peak, collapsed terrace walls, but subsurface volcanism pushed magma up through fractures in the crust and flooded the lava into the crater from below. It didn't spill over the walls. It came up from under the crater, and the volcanic uplift significantly modified the interior of the crater, often leaving it with a pattern of unusual rills on its floor. And these are very noticeable through even a modest telescope. Another type of crater are ghost craters. These are craters that existed before volcanism, flooded the Maria, and covered the flooding covered these pre-existing craters, and now we only see remnants of them, like Lamont, completely covered over, but the wrinkle ridges in the basalt reveal the original form of Lamont. Flamsteed P, almost 100 kilometers in diameter. All we see is the crown of the rim protruding. The same with Stadius, which is kind of hidden in the secondary crater field of Copernicus, but you can still see the circular rim protruding through the basalt. Another type of crater on the moon is a catena, a chain of craters. And this is an object that got broken up by the gravity of the moon or Earth and didn't strike as a single object, but struck as a long drawn out, broken up body where sequentially impact created a string of craters, all from the same common event. Now, let's crawl along the lunar terminator. Just past for a full moon, we're looking at the waning gibbous moon along this line of 60 degrees east latitude. We're going to see what we trip over just by going down this one line of latitude and see the tremendous variation of craters. They're not all the same. Each, like De La Rue, very old, pre-Nectarian, 136 kilometers in diameter. Below it, Endymion, kind of a plateau wannabe, another crater that's completely paved over like a parking lot with basalt. Also pre-Nectarian, very old, 4 billion years old. Masala, south of that, pre-Nectarian. Geminus, just above Mare Crisium. Eratosthenium, more modern. It looks more like a classic crater. It is a classic complex crater. Cleomedes, again, Nectarian, very old. Langrenus, again, classic complex crater, prominent central peak, collapsed terrace walls. Vendelinus, pre-Nectarian, very ruined, very old. Batavius, the Rima Batavius, that radial rill, really sets this one out as unusual and different. It's worth looking at. And then Snellius, Stevinus, Furnarius, a cluster of old and new. You can see Stevinus in the middle, obviously very much fresher, not as eroded, still a Copernican epoch, less than 1 billion years old. So, looking at other types of lunar features that show up very well in an amateur telescope, wrinkle ridges are known by the scientific name of dorsum or dorsa, and they are folds in Mare basalts that are caused by the slumping of lavas toward the center of a basin. the weight of the lava depresses the basin floor, so the lava's all slumped toward the middle and buckle up and form these fascinating wrinkle ridges that are only several hundred meters high. If the sun is too high, you can't even see it. There's no shadows. They're primarily visible right at sunrise when they do cast some shadows. They can be hundreds of kilometers long, but they're very shallow. The most popular wrinkle ridge is the serpentine ridge, which is the intertwining, the rope-like intertwining of dorsum Smirnov and dorsum Lister on eastern Mare Serenitatis. Dorsum Heim over on the western shore of Mare Imbrium extends downward from the Jura Mountains. And other unnamed wrinkle ridges look like frozen ocean waves washing into the horseshoe bay of Sinus Iridum. Like I said, some features on the moon are unnamed, such as the wrinkle ridges on eastern Mare Humorum. Rills on the moon are scientifically known as rima or rimae, and these are channels that are significantly longer than they are wide on the moon. And these are formed by 3 different processes, and they're all related to volcanism. A straight rill is formed by the slumping of land between 2 parallel faults. And this usually happens when a volcanic dike forces lava, a sheet of lava up from the molten core of the moon, splits the surface, but doesn't breach the surface as a volcanic eruption. So the land parts, the land in the middle collapses, and we end up with features like Rima Hesiotis on the bottom, or the extremely long Rima Cersalis on the left, on the right. Arcuate or curved rills, like those on eastern Mare Humorum, these are caused by stretching of the land at the edge of the Maria. The basalt depresses the basin floor and stretches it and pulls it apart and creates these curved rills around the rim of the entire Maria. And finally, the sinuous rill is formed by flowing lava, much like flowing water on the earth carves a channel in a riverbed or a stream bed. Flowing lava sliced through these and eroded these channels in the moon billions of years ago, and they're still there. Nothing changes them. There's no weather. No, they remain frozen in time. Now, there's another geologic feature called a scarp on Earth, but on the moon we call them rupas. And there's 2 ways these are formed. Some of them are the surviving cliffs that form the outer impact rings of impact basins. This example in this picture, Rupus Altai, is actually the single surviving arc of the outer Nectaris impact basin. The rest of it has all been obliterated by further impacts. But in this case, it's the remains of an impact basin. Other types of scarps are like Rupus Cauchi, are slumping between a fault. Rupus Cauchi is the lower of the 2 streaks. Rima Cauchi on top, Rupus Cauchi on the bottom. Think of it like the straight wall in the moon. Everybody knows about the straight wall, the giant cliff. It's a very similar feature. And speaking of straight wall, Rupus recta, over 100 kilometers long. In this case, it is casting a sunrise shadow. And again, the slumping of land from one side of another on a fault, creating a very steep slope. That past volcanic activity on the moon is visible in a number of ways. Pyroclastic deposits, sinuous rills like we just talked about, or cinder cones or volcanic domes that are visible on the moon. In this case, we're looking at the Aristarchus Plateau, very famous Schroeder's Valley, very prominent volcanic rill. And in the very middle of the moon, almost square in the center of the moon's disk, there's this pyroclastic deposits on the mountains just north of the Hyginus Rill, creates a dark area, kind of looks like a heart shape. So I call that the heart of the moon. And within some craters like Alphonsus, we can see the dark shading around cinder cones around the rim of the crater where volcanic vents have blown dark ash. Other regions like the Marius Hills, a huge collection of small volcanic domes, or Mons Rumker up on northern Procellarum. You look at it in the telescope and it kind of looks like a wad of gum stuck in a parking lot. Some sentimental lunar favorites. Everybody loves Plateau Crater. It just looks different. Started out looking very much like Tycho, but volcanism, subsurface lava flows filled the crater up with basalt, completely paved over the central peak, altered its appearance. Very unique. It becomes an instant favorite with everybody. When they label it, there's Plateau. It is on northeastern Mare Imbrium, Mare Frigoris just above it, Cassini crater down below, call it the snake-eyed crater. Two craters in the middle kind of give it a very distinctive appearance. Look at W Bond up there in the corner. Very squarish crater. Now, getting closer to Plateau, it's nestled into the Alps Mountains, the streak of the Alpine Valley next to it, little Pico and Piton mountains just below it, little set of mountain peaks poking up through Mare Imbrium that people love it. They're just little mountain peaks, but we fall in love with it for some reason. And then finally, notice Thor's hammer. See the little hammer shape? Yeah, for years, Agent Coulson was looking for Thor's hammer. Mjolnir was laying right in front of him all along. Anyway, even closer still to Plateau Crater. And now Tycho Crater, one of the youngest large craters on the moon, a little over 100 million years old. And it's nestled amongst some very old craters, Longomontanus, Clavius craters, 40 times older than this youngster. Getting in closer to Tycho, the territory around it highly pitted with tiny, tiny hundreds and thousands of secondary craters created by the material blasted out from the impact, showered out around, made hundreds and hundreds of small secondary craters. And you can see these in this close-up as well. The territory almost looks rusty with rust pits because of all these hundreds and hundreds of small impacts. Copernicus crater, one where we can see the ray structure from Earth. We can't see Copernicus itself. Our vision doesn't have that kind of resolution, but the blotch of the ray structure makes it very apparent. It's nestled in just south of Mare Imbrium, right below Eratosthenes and the Carpathian Mountains. And we can see the secondary craters from Copernicus, the shower of small craters created by the material thrown out by the Copernican impact. And Mare Insularum just to the west, one of the very last of the Mare named on the moon. It got its name in 1976. And then a Reinhold crater just for artistic effect in the picture. Straight Wall, just spoke about it, but it's one of the sentimental lunar favorites because it's such an unusual feature. It's a black line feature at sunrise when it's casting a shadow. At sunset, it's a white line as the cliff faces are brilliantly illuminated by the sun. It's on eastern Mare Nubium. Ersatzel crater up there, Thabit crater kind of mark the territory. And you notice that Straight Wall is kind of nestled in the middle of this circular structure. On the left, we see the horseshoe bay effect of a crater rim that has been overlaid by the Nubian basalts and wrinkle ridges forming the rest of the arc. We like to call that hidden crater ancient Thabit. It has no official name, but we call that territory ancient Thabit. Now this picture, Straight Wall, at sunset. Contemplate this for a minute. If you're standing on top of Straight Wall, looking out across the plains of Nubium, watching the sun go down, the moon rotates much slower than the Earth does. On Earth, we watch the sun, the ball of the sun, set within 2 minutes. The moon takes a lot longer to rotate. That sunset on the moon would take 1 hour. That's a long time to contemplate the beauties of what you're watching. Sunsets on Earth create reams of poetry and prose and beauty and art. but watching that sun go down for a full hour gives you a long time to reflect. So, we'll get to conclude this with looking at some nicknamed features on the moon. Not all features on the moon have official names. They're popular. It's like deep sky features. We give them particular names to endear them to us. But we do the same thing with lunar features. My lunar good luck charm, the overlapping forms of 4 separate craters of the Meton complex. They each have a Meton B, C, D, but when they all overlay and are commonly filled in with debris, forms this lunar good luck charm. I claim naming rights on that. The guardians are the 2-kilometer massifs on either side of the gorge that empties out into Mare Imbrium from the Alpine Valley. Now, Chuck Wood, the Sky and Telescope moon columnist, he's the one who named that. And another one that I claim, Thor's hammer. That's mine. Yeah, the Python Gamma is what it's officially called, but it so much resembles Mjolnir, the hammer wielded by the mythical Norse god Thor. It just begs for a name. It's Thor's hammer. The Valentine Dome on the eastern Mare Serenitatis, very low pancake-shaped volcanic dome, about 30 kilometers across, barely more than a kilometer high. Takes very low sun elevation to see it. Kind of resembles a Valentine shape. We call it the Valentine Dome. Cobra Head, the volcanic where the lavas flowed from the Aristarchus Plateau down Schroeder's Valley and emptied out onto Oceanus Procellarum. We don't know who named that one, but they did a good job. Another one of mine, the heart of the moon. This mountainous region just north of Ramon Hyginus has no name. So it has a heart shape. It looks like a Valentine heart. It almost looks like a human heart. So it's the heart of the moon. The lunar spider, Lamont, the ghost crater. The radial wrinkle ridges radiating out from it gives it the spider appearance. And the ghosts of Procellarum. Oceanus Procellarum, before it flooded with lava, it had just as many craters as the rest of the moon, and now only their rims protrude above the smooth lava plains of Oceanus Procellarum, so we call them the ghosts of Procellarum. And ancient Thabit, which I just explained, so I won't go too farther on that. And the railroad tracks, the parallel rays extending northwest from Tycho crater. Now, in conclusion, I like to say that the moon is ever changing. It is not a static target. It is not the same moon every night. The phases grow and shrink day by day. The shadows change hour by hour. The series of photographs across the bottom, you notice how radically the shadow pattern changed across Ptolemaeus crater. That is over a period of 2 hours. It changes that fast. Like I said, shadows change hour by hour. The moon is a geologic wonderland. And it's the only world that we can see from our backyard in a modest telescope with kilometer resolution and recognize these geologic patterns on another world with our own eyes. So, main thing is the moon is accessible from your backyard. The moon does not care about light pollution. You can observe the moon in daytime. So it's a very viable target, and it breaks my heart that people ignore it. So there's much to live on the moon, and I invite you to come join me on my playground. Thank you very much.